Okay, so this is our review session for exam number 4. To start out, we'll talk in general about the exam. It's going to be a little different from our other exams because you'll be taking it home over Learning Suite as opposed to taking it in the testing center. And then we'll do a review of the topics that we have covered that will be on exam 4. So exam number 4 is going to have 2 parts to it. And because the rules for taking those parts are going to be different, you're going to take those parts separately. Part 1 is going to be the multiple choice, but there's going to be more multiple choice questions than normal. We're going to have 26 multiple choice questions worth a total of 78 points, or 3 points each on those multiple choice questions. You will have 1 hour to take the multiple choice portion. That's going to be in Learning Suite. We're going to use the Simple Proctor system, which uses your web camera to take pictures of you at certain intervals to make sure you're looking at the screen and not looking at something else, or perhaps looking at paper. But be aware that we will use the Simple Proctor system. And what that also does is it detects if you have opened anything else, any other browser windows on your computer other than the one that you were using with Learning Suite to take the exam. So it strongly discourages you from using the internet to cheat on your computer. So you'll have 1 hour to do the multiple choice, and it'll be a little bit longer than our typical multiple choice sections. And then the second part of the exam will consist of 2 short answer questions. Okay? One of them will be a synthesis problem, and then the other one will just be a miscellaneous short answer problem. It might test mechanisms, it might test other concepts that we have learned. Those 2 short answer problems will be worth the remaining 22 points on the exam. They'll be a little bit more challenging than the short answer questions we've had on our regular exams. And so they will be open book, open notes, okay? But it's not open Chegg. I repeat, you cannot use Chegg, you cannot use resources other than your textbook and your class notes for the 2 short answer questions on the second part of the exam. That will also be inside of Learning Suite. So what you'll do is you will upload pictures. You'll write on your own paper the answers to those short answer questions. And when you've completed them, you will be able to use your phone to take pictures of the papers, and then you can upload those pictures to Learning Suite. You will have an hour and a half to do those 2 short answer questions. Even though they'll be challenging, I'm confident that an hour and a half is plenty of time for you to work those 2 problems, okay? You will be required to have a proctor for this exam. And so one of the other things we'll do on the short answer is we'll ask you to write down on a piece of paper the name of your proctor, contact information of your proctor, and also to certify that you did not cheat while you were taking either of the 2 sections of the exam. And so you'll upload that information as part of the short answer part 2 of the exam. And what the proctor will do is they will certify that at the beginning, or that while you're taking the multiple choice portion, that you did not have class notes, you did not have a separate electronic device such as a phone that you were using. They'll certify that you didn't have anything else, that you just took that multiple choice section under the same situation that you would take the exam in the testing center. I will mention that you can use a periodic table. I'll post a periodic table on Learning Suite, and you'll be able to download that and print it out before you take the exam. So you're able to have a periodic table and scratch paper. But that's all that you can have for the multiple choice section of the exam. So the proctor will verify that that's all you had for the multiple choice section. They don't have to watch you the whole time, but they should check on you periodically and then they also will verify that you didn't use any unauthorized internet resources for the second part of the exam. Okay, so that's how it's going to work. A little bit different because you're taking it at home. So altogether, we'll have a time limit of 2.5 hours split up into 1 hour of multiple choice, 1.5 hours of short answer, a little bit shorter time limit than we're used to because it'll have more multiple choice and less short answer questions. It will be open on one day and one day only. So it will be available on Thursday, and that's Thursday, December 10th, I believe. So next Thursday. It will be open from 8 a.m. to 10 p.m. Mountain Time. And that just matches the normal hours of the testing center. So it would be just like having one day to take an exam in the testing center. 8 a.m. to 10 p.m. On Thursday. So sometime in those 14 hours, and remember that's Mountain Time, some of you are in different time zones, so you need to make sure that you're taking it during that window. Sometime during that 14-hour window, you need to budget 1 hour to take the multiple choice, and then 1.5 hours to take the short answer. You can split it up if you want, or you can just go right through, finish one section, and do the other. But you need to finish one section before you start the other section. Okay. So if you have any questions about that, I will be sending out an email next week with those instructions. But you please feel free to send me emails if you have any questions or concerns about the way we're doing Exam 4. So the way to study for Exam 4 is going to be similar to how we studied for the other exams because it's more heavily weighted towards multiple choice questions. There will be less of drawing mechanisms than we've had on our last couple of exams. However, there are plenty of ways of using multiple choice questions to test your understanding of mechanisms. So you still need to have a very good understanding of the mechanisms we've learned in this section. There are less of them because of spectroscopy. We only have 2 chapters where we learned reactions, chapter 12 and chapter 15. But you do need to know those mechanisms. You do need to know the reactions, even though we're probably not going to have questions where you draw the products. There are ways to ask you to predict products in multiple choice questions and to provide reagents. So you'll want to study the reactions in the same way that you've studied the reactions for our last 2 exams. As far as the spectroscopy material, the best way to study for the spectroscopy material is to work the take-home spectroscopy quiz. The take-home spectroscopy quiz is a comprehensive spectroscopy quiz that combines all of the different analytical techniques we've learned. IR, mass spec, proton NMR, C13 NMR. So by doing the spectroscopy quiz, which is due on Monday, then you will be studying and preparing for the spectroscopy components of Exam 4. There are a few additional things that you'll want to do, and we'll hit that. We'll mention those when we get to Chapter 13 and Chapter 14 in our outline. But I'll just tell you that, first of all, the number one thing you want to do to prepare for the spectroscopy part is to work the spectroscopy quiz. So with that, let's go through our chapters and make outlines of the key topics that we learned in each chapter. So the first chapter for this section was Chapter 12, Oxidation and Reduction. The first thing we learned in this chapter is the definitions. We defined oxidation and reduction a bit differently than you're used to defining them in general chemistry, based on changes in the numbers of carbon heteroatom bonds as well as carbon-hydrogen bonds. So being able to define oxidation and reduction is an important part of this chapter. We talked about reduction first, and we had types of reducing agents. We said that there were three ways. We said that our reductions were all involving the delivery of hydrogen, or H2, to a molecule. And we had three ways of doing that. We could use hydrogen itself along with a metal catalyst. We could deliver protons and electrons separately using single electron transfer chemistry. Or we could deliver hydride, H minus, followed by a proton, H plus. Okay, so there are different types of reducing agents that accomplish reduction by those methods. Then we started talking about reduction reactions, and the first one we covered was hydrogenation. Okay, and hydrogenation was using hydrogen and a metal catalyst. You'll remember we learned a mechanism for this reaction, but it was a different sort of mechanism. It didn't involve curved arrows. It's our only mechanism that actually involves a cartoon drawing. So it is important to understand that mechanism because that mechanism tells us important things and is consistent with the data from the hydrogenation process. That mechanism helps us understand the role of the catalyst, serving as a surface to bring the reactants together. The mechanism helps us understand why we have a syn addition. The hydrogenation is also an addition reaction, and it is a syn addition. And we can understand why if we understand the mechanism. And it also helps us understand the relative rates. We learned that less substituted alkenes will react faster. And if we understand the mechanism, we understand why that is the case. All right? Let's come over here for our next topic, which was the reduction of alkynes. So with alkynes, we had three ways that we could reduce them, three different outcomes. If we use hydrogen and a metal catalyst such as palladium carbon, we would generate an alkane. We would reduce an alkyne to an alkene, and then the alkene would get reduced to the alkane. We could use hydrogen and the Lindlar catalyst, and that would generate a cisalkene. Remember, that is our poisoned catalyst, the one that is less reactive. So it reacts with an alkyne. Alkynes are generally more reactive than alkenes. And so the poison catalyst reacts with alkynes, but not alkenes. Because hydrogenation is a syn addition, we obtain a cisalkene. And then the third method we learned for reducing alkynes involved the use of sodium and ammonia, and that gives us a transalkene. And remember, this involved single electron transfer chemistry, where the sodium atom will collide with an alkyne, and transfer its electron. Okay. So three different ways of reducing alkynes. We need to know the products. We need to know the mechanism. We drew a mechanism for this one. These two mechanisms are just the cartoon mechanism that we learned for hydrogenation of alkenes. And then our last reducing agent we learned about was lithium aluminum hydride. This is one of our metal hydride reagents. Remember when we draw the aluminum hydride ion, the formal negative charge is drawn on the aluminum atom, but we said that the negative charge is really located on the hydrogens. So this functions as a source of hydride, or negatively charged hydrogen. And it was used to reduce alkyl halides and epoxides. Okay? And that was simply an SN2 mechanism, but that was our last reducing agent that we learned about. Okay? All right, so the remainder of the chapter focused on oxidation. So we learned types of oxidizing agents. And we had two types of oxidants, those that contained an oxygen-oxygen bond. We said that the oxygen-oxygen bond is weak, and it is cleaved in all of the oxidations that we learned in chapter 12. And then our second category of oxidants were those that contained a metal oxygen bond. Okay. So we had several oxidation reactions that we learned in this chapter. The first one was epoxidation. And the epoxidation reaction uses peroxy acids as the oxidants. Compound an oxidant with an oxygen-oxygen bond. The most common peroxy acid is MCPBA. So you can use the abbreviation. You'll probably see the abbreviation. But if you were asked to draw the mechanism or understand the mechanism, you would want to know the structure of that compound. So remember, key things with epoxidation. It's a concerted process. One step, but there was a whole bunch of arrows moving, electrons moving, a whole bunch of curved arrows in that step. And it is a syn addition. And because it's a syn addition, it's stereospecific. That's a term we learned earlier in the class, meaning a specific isomer of an alkene will give a specific isomer of the epoxide. Okay. Then our next oxidation was the dihydroxylation. This is where we are adding two OH groups, one to each of the carbons of our alkene. And there were two ways to perform a dihydroxylation. We could perform a dihydroxylation with anti-stereochemistry, and that's a two-step process. We have to epoxidize first, and then we have to open the epoxide with OH minus. Okay, so we have a syn addition in the epoxidation, and then we have inversion when we open the epoxide with hydroxide. The net result is an anti-dihydroxylation. And then if we need to perform a syn dihydroxylation, that's where we use osmium tetroxide. I told you to do that in combination with NMO, which is a stoichiometric reoxidant. And then you use NaHSO3 and water. The entire mechanism of this syn dihydroxylation is complex, and so we only taught you the first step. We showed you the cycloaddition step, the reaction between the osmium tetroxide and the alkene, and that cycloaddition step explains why the dihydroxylation gives us syn stereochemistry. Okay, so the next oxidation reaction we had was our oxidative cleavage. Also known as ozonolysis, where we used ozone to cleave the carbon-carbon pi and carbon-carbon sigma bonds of alkenes. And so we generated aldehydes and or ketones, depending on the alkenes we started with. This was another reaction where we only learned the first step of the mechanism. So you only have to be responsible for the first step of the mechanism. You should know the reagents. In addition to using ozone, you have to use a reductant, either zinc or dimethyl sulfide. And then the other skill that's important to have that's related to oxidative cleavage is, given the products, the aldehyde or ketone products of an oxidative cleavage, figure out what alkene gave those products. Okay, that's a fairly common type of question that you see. Then our next oxidation involved oxidizing alcohols. Okay. So with the oxidation of alcohols, we have different types of products that we can obtain depending on the alcohol we start with. And with primary alcohols, we have different outcomes depending on the oxidant we are using. PCC will oxidize a primary alcohol to give an aldehyde. Our other chromium-based oxidants used together with sulfuric acid and water will give us a carboxylic acid. Okay, so you need to be able to predict the outcomes of reactions depending on what kind of alcohol you're starting with, primary or secondary. Remember, tertiary cannot be oxidized. And what reagents you're using. You also would need to know which reagents would give you the desired product of a specific oxidation. You should know the mechanism. Again, drawing mechanisms is not going to be as big a part of this exam as it is for other exams, but knowing mechanisms is going to be a big part of this exam. So you'll see questions testing your mechanistic understanding on the multiple choice section. So the good news is that there was just one mechanism we drew for the oxidation of alcohols, regardless of which of the reagents we used. And then you should also know why PCC gives us an aldehyde from a primary alcohol, whereas chromium trioxide or dichromate in the presence of sulfuric acid and water gives us a carboxylic acid. And that was due to the fact that we could generate a hydrate intermediate from an aldehyde when we had acid and water present, and then that hydrate could undergo oxidation to the carboxylic acid. When we don't have water present with the PCC oxidation, we don't form the hydrate. Okay, so those are all the topics we learned related to the oxidation of alcohols. We talked about green chemistry, and I'll just put that up here because that is a very popular buzzword these days. And so it's important to understand the definition of green chemistry. Probably not going to be a huge factor on exam 4, but the American Chemical Society recently has loved to find ways to slip green chemistry into its standardized exams. So just make sure you're familiar with the term. That'll be a bigger factor when we get to the final. And then we concluded chapter 12 with the Sharpless asymmetric epoxidation. This was our first reaction with a chiral catalyst, the first reaction that can take an achiral starting material and generate a single enantiomer of the product instead of giving us a racemic mixture. I'll repeat what I told you in class, which is do not waste a second memorizing the mnemonic device that is in the book. It is not valuable to memorize the mnemonic device. If you were ever running one of these reactions in the lab and you needed to know which enantiomer of the catalyst would give you which enantiomer of the product, you could simply look up the mnemonic device. Even if you memorized it, you probably wouldn't trust your memory. You'd look it up anyway. So it's a complete waste of your time to memorize that mnemonic device that is in the book. The only reason it's there is that it's easy to test, but that's kind of a cop-out in my opinion. So we're not going to do that. What we focused on with the sharpless asymmetric epoxidation is understanding the concept behind this and other enantioselective reactions. We answered the question, how is it possible to generate a major enantiomer and a minor enantiomer in a reaction? If you'll remember, we drew an energy diagram. It looked like this. We had a starting material in the middle. We had a pathway leading to our major enantiomer. We had a pathway leading to our minor enantiomer. We noted that the two enantiomers were equivalent in energy. So if we were relying on thermodynamics to control the process, we would always get a one-to-one mixture of those enantiomers. The only way to get a major enantiomer and a minor enantiomer is to use kinetics to make sure that the pathway leading to the major enantiomer is faster than the pathway leading to the minor enantiomer. And the way we do that is we use a single enantiomer of a chiral catalyst, which causes our two transition states to be diastereomers of each other. As we learned earlier in the class, diastereomers are not equivalent in energy. So one of these diastereomeric transition states is lower in energy than the other, allowing our major enantiomer to be formed faster. That is what's most important about the sharpless asymmetric epoxidation. So please focus on that concept and not on memorizing any mnemonic devices. Okay, let's move on to chapter 13, mass spec and IR. That was the shortest chapter of this section of the class. And we started with mass spectrometry. And so the first thing we did was we spent some time explaining what a mass spectrometer is and how it works. It is important to have a basic understanding of each of the instruments that we discussed in chapters 13 and 14. So with a mass spectrometer, you need to understand what's happening inside the instrument. We're ionizing our sample. How do we ionize our sample? We bombard it with high energy electrons that knock an electron off. And what do we detect? We're detecting the mass to charge ratio of the ions that are forming. Okay, so just understanding the basics behind how the instrument works is important to understanding the information that we obtain from that instrument. We then looked at mass spectra. A few things we noted. We, of course, looked for the molecular ion, but we also noticed that there was a small M+1 peak, 1 atomic mass unit higher than the molecular ion. We need to understand why we see an M+1 peak in the mass spectrum. We introduced the nitrogen rule. The nitrogen rule is very valuable. If you have an odd molecular weight, you know that you have an odd number of nitrogens in your molecule, so that's quite useful. We learned that certain alkyl halides will give an M+2 peak in the mass spectrum. And the ratio between those peaks will differ depending on the type of halogen you have, a chlorine or a bromine. So that's also very useful. Okay, so those are some of the key points related to mass spectrometry. The next thing we learned in chapter 13 was about electromagnetic radiation. The electromagnetic spectrum and the different types of radiation in that spectrum, all the way from radio waves to gamma rays. And so the important thing, this is material that you've learned in other classes, so we didn't spend too much time on it, but we did focus on the relationships between some key parameters, the relationships between wavelength and frequency, as well as energy. Okay, so we know that wavelength and frequency are inversely proportional. We know that frequency and energy are directly proportional. So higher energy radiation has a higher frequency and a smaller wavelength. Okay, so those were the key things in regards to electromagnetic radiation. Okay, then we went on to IR spectroscopy. So the first thing with IR spectroscopy is, what is it telling us? We're using it to identify functional groups. Okay. How are we identifying the functional groups? What type of electromagnetic radiation are we using? We're using infrared radiation. Longer wavelength, shorter, so IR radiation is going to have, longer wavelength and lower frequency, lower energy than visible light. And what is happening when the IR radiation hits our molecule and the molecule absorbs the IR radiation? We're having vibrations occur. And those vibrations involve stretching or bending of bonds. Okay, so that's the background. And then we also learned or reviewed Hooke's law. To understand the relationship between bond strength and the absorption frequency, the relationship between the atomic masses of the atoms that are involved. So understanding Hooke's law helps us understand the relative positions of the stretches of different bonds in the infrared spectrum. So we don't have to memorize a lot of numbers. There's only two values that I told you you should memorize. 3,000 wave numbers, right? And that's valuable for two reasons. We have the OH or NH stretch, and that's going to be a very broad, very fat peak above 3,000. And then you also have your SP2 or SPCH stretches above 3,000 versus your SP3CH stretches that are just below 3,000. So two reasons why 3,000 is important. And then we told you that 1,700 is our other important number. That's where our carbon-oxygen double bond or the carbonyl stretch appears. And remember that that stretch is a very strong signal. So those are the only two numbers you should memorize. 3,000 is significant for two reasons. 1,700 is significant for one reason. Anything else? Just understanding the trends is important. So this table in your book, figure 13.10, does a great job of just dividing the IR spectrum into four categories and putting the different types of bonds in those different categories, and then letting us know why those different types of bonds appear in those categories. And it's all based on Hooke's law. So if you understand why the different types of bonds are in those different categories based on Hooke's law, then you have a good understanding of the fundamentals underlying IR spectroscopy. Then the last thing with IR to note is the effect of symmetry we told you that for a bond to absorb IR radiation and stretch, that there has to be a change in the dipole of that bond. And so the consequence of that is that a symmetrical alkyne doesn't absorb and will not give a peak in the IR spectrum. Okay, so the effects of symmetry on IR spectroscopy. Okay. All right, so that was it for chapter 13. Let's move on to chapter 14, NMR spectroscopy. And NMR spectroscopy is our most useful technique. It gives us the most information. Of course, IR and mass spec are valuable, and we use them together with NMR. But if we were to pick one technique that gives us the most information about the structure of a molecule, it would be NMR spectroscopy. So, as I mentioned to you, the take-home quiz is going to help you prepare for the exam. Largely will help you prepare for most of what's in chapter 14. But let's just go through this outline. So again, as we did with mass spec and IR, we need to understand the background or the theory behind NMR spectroscopy. So we learned about nuclear spin states. It's important to understand about nuclear spin states, the fact that we have to have two nuclear spin states, +1/2 and -1/2, in order to observe nuclei by NMR spectroscopy. We learned about the spin flipping process. And that's what allows us to observe peaks. We also learned that a magnetic field is necessary. We also learned that radio waves are the type of radiation we're using, radio frequency radiation. I drew a diagram for you. It looks something like this, with magnetic field strength on the x-axis, energy on the y-axis. So you should understand the significance of this diagram. Namely, that depending on the field strength that a given type of hydrogen atom or proton is feeling, there will be a difference in energy between those nuclear spin states, and that will cause the signal for those protons in the NMR to show up at a slightly different position. Okay? And then we learned about the chemical shift scale. And there were two terms we learned. Remember, the physicists got this backwards for us. Downfield is a higher chemical shift, or de-shielded. Upfield is a lower chemical shift. You might see these terms, and so it's important to understand these terms if you're going to see them on an exam. Okay? So there were 4 key features of a proton NMR spectrum, and there was information that we gained from those features. The first one was the number of signals in the spectrum. And we said the number of signals is the number of different types of protons. Okay. And in some molecules, it's easy to tell the number of different types of hydrogens. In others, it's not quite so straightforward. We had 3 terms that we learned along with this. We learned about homotopic hydrogens. We learned about enantiotopic hydrogens. And we learned about diastereotopic hydrogens. So it's important for you to be able to identify pairs of hydrogens as being homotopic, enantiotopic, or diastereotopic, and knowing which ones are equivalent in the NMR, which ones will give a single signal, and which ones are not, which ones will give multiple signals, okay? Second thing we learned, or the second key feature of the NMR is the position or the chemical shift. That's the position of our signals. That tells us what types of hydrogens are present. Okay. And so associated with chemical shift, we learned the terms shielding and de-shielding. We learned that nearby sigma and lone sigma electrons and lone pairs can shield protons from the applied magnetic field. We learned that electronegative heteroatoms can pull on electrons and de-shield those protons. And so we have a chemical shift range of where different types of hydrogens will show up. We had a table in the book of those chemical shift values, and I would encourage you not to memorize the values, but instead to understand the order. Okay, let's pull up the key figure here. So here's the table that shows the values. This is helpful when you're working on the take-home quiz, and you can use this table on the take-home quiz. But for the exam, rather than memorizing numbers, being able to know the relative order from left to right of the given types of hydrogens is more important. So what's more important is understanding a figure such as this. So in this figure, we've divided the spectrum up into 6 regions. And you should know why aldehyde hydrogens and carboxylic acid hydrogens are the most de-shielded, the furthest downfield. You should know why hydrogens attached to sp3 carbons are the most shielded, the most upfield. And then you should understand the positions, the relative positions of these signals, not necessarily the numbers, but the relative positions, okay? So if you can look at a structure and you can put the hydrogens in order in the spectrum, that's the skill that you'll need for the exam, not necessarily memorizing the numbers, okay? And that is understood by considering the impact of the sigma electrons in the lone pairs, the impact of electronegative heteroatoms or allylic sp2 carbons, like here, and then finally the impact of pi electrons. We learned that the pi electrons in a benzene ring and an alkene will de-shield the hydrogens attached to those sp2 carbons. In contrast, we learned that the pi electrons in an alkyne will shield a proton attached to an sp carbon. Okay, so understand the trends, understand the underlying reasons for the trends, because if you understand those underlying reasons, you're not just memorizing this figure. If you memorize this figure, that's not nearly as good as understanding the figure. Okay, so let's go back over here and look at our third piece of information we get from an NMR spectrum, and that is integration, or the intensity of those peaks, the area under each peak. That tells us how many of each hydrogen we have. And we went through an example of how you would convert integration values into a number of hydrogens. You would have to know the molecular formula in order to do that. So you would determine the molecular formula from mass spec data, or in some cases, the molecular formula would be given to you. You figure out how many integration units represent a single hydrogen atom, and then you use that info to determine how many hydrogens are in each peak. Okay? And then fourth, we had splitting. The splitting of the peaks into doublets, triplets, quartets. That's telling you number of neighboring hydrogens that are non-equivalent. Okay? So there's a lot of important things in regard to splitting that's important. So we have the n+1 rule, where if we have two neighbors, we're going to have a triplet. One neighbor will have a doublet. We went over the reason for that. It has to do with the different spin states of those neighboring protons and the different combinations of spin states that we have. So it's important to understand that. We also had common splitting patterns. We'll come back over here and show you another figure from the book. This one right here, table 14.4, are common splitting patterns that correspond to certain types of subunits in a molecule. And you should definitely not be memorizing these. If you understand the n+1 rule, then you understand if you have two doublets, that means you have two CHs that are next to each other that are not coupling to anything else. You understand that if you have a triplet and a quartet, you have an ethyl group, okay? So do not memorize this. If you understand it, that's a sign that you understand splitting and you understand the n+1 rule, okay? Then we had the concept of non-equivalent neighbors. And with non-equivalent neighbors, we had a more complex splitting pattern, which was n+1 times m+1, okay? So we ended up with more peaks in our molecules. Again, I'll come over here and show you the figure. This figure right here, where we derived the n+1, m+1 rule. This is where the non-equivalent neighbors are splitting this signal, HB in this case, differently with different J values. And so we end up with more peaks. Okay, so it's important to understand the reasoning behind this, why we obtain this. Okay. All right, then we had the characteristic J values or coupling constants of alkenes. We taught you that if you have geminal hydrogens on an alkene, you have a small coupling constant. Cis hydrogens give you a medium coupling constant. Trans hydrogens give you a large coupling constant. Okay, and we went over an example in class of how you can use those different values to assign the peaks in the proton NMR. And then finally, on splitting, we learned that if you have an OH or an NH, you have no splitting caused by those signals, and those signals are not split by their neighbors. And we talked about why that is the case. Okay. All right. And then the final thing on NMR, we'll come over here. The final topic that we learned was C13 NMR. And we spent much less time on C13 NMR than on proton NMR. Some of the key things here: 1.1% natural abundance. So the C13 atom is not very abundant. So that means that The technique is not nearly as sensitive. The baseline is much noisier as a result. We also learned that there's no splitting or integration. It is possible under some circumstances to obtain splitting information from the hydrogens attached to that carbon, but in most cases, there's no splitting. We just see singlets. There's no integration because the intensities of the peaks do not correspond to the number of carbons represented by those peaks. And then we told you the most important use of C13 is determining the number of different types of carbons. You can also get chemical shift information from C13, but in my opinion, it's easier to use proton NMR for that. So what you want to do with a C13 is count the number of carbons. You should know the number of carbons in your molecule when you're doing this. If the number of carbons in your C13 spectrum is less than the number of carbons in your molecule, you know that some of your carbons are equivalent due to symmetry. So you know that you have some form of symmetry in the structure of your molecule. So that's what C13 is useful for. And we went over an example in class showing you how that could be useful in determining structures. Okay, let's go on to our final chapter, chapter 15, radical reactions. So in this chapter, we started out with similarities between radicals and carbocations. We said that they had similar structures, trigonal planar. We classified them in similar ways. Their relative stabilities were similar, where more substituted radicals are more stable. So it's helpful to consider the similarities between radicals and carbocations because that helps us understand the structure, since we've already learned many things about carbocations. We also learned about bond dissociation energy as a measure of radical stability. If we have a lower bond dissociation energy, that tells us that the radical that results from cleavage of that bond is going to be lower in energy or more stable than if we have a high bond dissociation energy. Okay. Another general feature, we learned about the requirement for heat, light, or an initiator. Okay. One of these three things is going to be required for a radical reaction to take place. Then we learned about typical processes that occur in radical reactions. We learned that once we've generated a radical, it can abstract a hydrogen atom from an alkane. We've seen that in most of our radical reactions that we studied in this chapter. And then we also learned that radicals can undergo addition to alkenes. We saw that in the radical addition of HBr to alkenes. Okay. And then we learned about radical scavengers, antioxidants, something we learned about later in the chapter. Those are radical scavengers. They will intercept a radical intermediate and form a more stable product. So oxygen, BHT, vitamin E fit in this category. And we later learned why those species inhibit radical reactions. So after we learned these general things about radicals, we went into some specific reactions. We started with the halogenation of alkanes. So this is the one process we have of reacting an alkane and introducing a functional group on an alkane. So it is very useful if you have a synthesis problem that requires you to start with an alkane, you know you're going to use a halogenation reaction, okay? It's very likely that you will have such a synthesis problem. I'll just go ahead and tell you that right now. So the mechanism of this reaction is important. And remember, we have 3 different types of steps. We have initiation, we have propagation, propagation. So if we're drawing a mechanism for a halogenation, we would only draw the initiation and the propagation steps. But it's important to know that we occasionally do have termination steps occurring. So being able to recognize those steps where 2 radicals would come together. But if we're drawing a mechanism, we're usually just drawing the initiation and the propagation steps, okay? All right, so let's talk about the specific reactions we learned, the 2 specific halogenations. We have the chlorination. Let's go over here. Okay. So what was unique about the chlorination compared to the other halogenation we learned, the bromination? So in the chlorination, our rate determining step is exothermic. The hydrogen atom abstraction by the chlorine atom is exothermic. According to Hammond's postulate, that means the transition state is more like the reactants than the products. And so there's not a big difference in rate for forming a more substituted radical versus a less substituted radical. So remember, the consequence of this is that all possible products are formed. Okay. So we will form the more substituted halides faster, but because there's always less hydrogens leading to the more substituted products, due to statistics, we end up with all possible products from chlorination formed in roughly equimolar ratios. Okay? So we learned that chlorination is only useful for giving a single product when all the hydrogens in the molecule are equivalent to each other. Methane, ethane, cyclohexane, these would be examples of molecules where that would be useful. Then we had the bromination reaction. In the bromination reaction, that rate determining step, the abstraction of a hydrogen atom from an alkane by a bromine atom, that step is endothermic. So according to Hammond's postulate, the transition state more closely resembles the products or the radicals. And so there's a much bigger difference in energy, in activation energy for forming a more substituted radical versus a less substituted radical. As a result, in the bromination, you get the more substituted product only. Actually, the example we showed you was 99:1, but it's essentially giving you only the more substituted product, okay? So bromination is only useful when you're trying to generate a single secondary bromide or perhaps a single tertiary bromide. If there's one more substituted bromide that you can make from your alkane, then bromination is going to be very useful, Okay. We talked about the stereochemistry of halogenation. We said that if the reaction is occurring at a stereocenter, you will obtain a racemic product because that radical is achiral. We said that if the alkene, starting alkene is chiral and the reaction is occurring at another carbon in the molecule, that you would generate a mixture of diastereomers. So we went through examples of stereochemistry and how it impacts radical halogenation. Okay. Then we talked about the ozone layer and radical chemistry that occurs in the ozone layer. The key thing to remember there is that a single chlorine atom can destroy thousands of ozone molecules. Because it's a chain reaction, we're able to destroy thousands of ozone molecules with a single chlorine atom derived from a single chlorofluorocarbon. So that's why chlorofluorocarbons have been phased out, because they are so dangerous to the ozone layer. Okay. Then we learned about allylic bromination. Using NBS. So we learned about how allylic carbon-hydrogen bonds are weaker than other sp3 carbon-hydrogen bonds due to the resonance stabilization of that radical. And that allows us to use N-bromosuccinimide to perform an allylic bromination reaction. We have a low concentration of bromine delivered by that reagent. We have either one or two possible products, depending on whether our allylic radical, if the resonance structures are equivalent or not. Then we learned about the oxidation of unsaturated fatty acids. That involves oxidation at allylic carbons, generation of allylic radicals by oxygen abstracting hydrogen atoms. Okay. And then in conjunction with that topic, we learned a bit about antioxidants, which are a type of radical scavenger, something that we defined earlier in the chapter. But we learned about BHT and vitamin E and how those function as antioxidants, how BHT is a biomimetic molecule. Then we learned about the radical addition of HBr to alkenes. Okay. So we learned that peroxides are required. Initially, they were present as an impurity in the alkenes, and chemists were surprised when this reaction occurred and generated the less substituted alkyl halide. Okay? So you should understand the mechanism of this reaction. You should understand why it is giving the less substituted alkyl bromide, as opposed to the more substituted bromide, which forms when we don't have peroxides present in the non-radical mechanism. And then you should understand why this reaction only proceeds with HBr, why it doesn't work with HCl or HI. Okay? And then the last thing we talked about is polymers. And with polymers at this stage, the skill that we need to have is being able to connect the structure of a monomer with the structure of the polymer that can be made from that monomer, and vice versa. Given a polymer structure, figure out the structure of the monomer that was used to make that polymer. So this concludes our review for exam number 4. Good luck.